21,991 and some change, right? Let's just go with that. Let's go with 21,991 what, though? Inches per minute, good. Inches per minute. Is that fast? Well, again, we'd have to go back to what we know, what's relative to us that makes the most sense. So I think I'll do a quick conversion. I could go and do all my conversion factors, or I could just ask my phone again. Okay, Google. Isn't technology great? Oh, I asked. They don't understand. Yes. Okay. No, they disagree. Convert 21,999. Cannot compute. Convert 22,000 inches per minute to miles per hour. I'm just rounding this up to 22,000. 20.8 miles per hour. It's about 28 miles per hour. Not too bad, right? Not too bad. Yes?
If there was a problem like that, would you want us to convert to miles per hour or just leave it at?
I could. Yep. That's why I showed you one to be able to do. Do you all want to see how to convert this, or you okay with it? Or it's your call. It's your. I expect that you can. I'm just cutting down on time by doing it with my phone. Do you want to or not?
Let's do it.
Okay. Let me do 22,000 inches. I'm going to go to IN instead of this little symbol. IN, inches per 1 minute. Okay, here we go. I'm going to go fast though. Okay, let's get rid of minutes. I need to go from minutes to hours. How many minutes are in an hour? 60. So I multiply 60 minutes on top, 1 hour on the bottom, and that should get rid of my minutes, and I'm good to go. Okay, how many? I'm trying to get from inches now to where? Miles. I don't know conversion easily from inches to miles, but I do know inches to feet, and I do know feet to miles. So first I'm going to go inches to feet. If I want to get rid of inches, I know I need to put it on the bottom because it's on the top over there. So 12 inches is 1 foot. And now if I want to get rid of feet, I need feet on the bottom. And how many feet are in 1 mile? 5,280. 1 mile. So that might be something that you start to try and memorize, how many feet there are in a mile. And then if you multiply straight across, you cancel out your inches canceled and minutes canceled and feet canceled, then you should get something close to 28 miles per hour. All right. What I think is crazy is like, y'all know what a Blu-ray player is, Blu-ray disc player? Does everyone even watch Blu-rays anymore? I don't know. Are we past that? So the way that works is you have like a DVD, right? And you've got this little arm that reads it, and this thing spins, and it has all the little zeros and ones on there, and it tells this little reader what to project onto your screen, right? So that thing is spinning. And it can spin at speeds up to 10,000 RPM. 10,000 revolutions per minute. So think about taking that. If I divide that by 60, that's 166 revolutions. 166 revolutions per second. Right? That's pretty fast, right? That's pretty quick. So when you look at like jet engines, those things are spinning really fast in there, and then you have a failure. Something in there breaks. All those fan blades get thrown out. It's because they're spinning. They don't want to be there. They want to go out. and it breaks and everything gets thrown out and it totally destroys the engine and the aircraft, and that's not good. But things spin very fast. In fact, when you're driving your car, right, most of us have an RPM gauge, revolutions per minute. It's telling you how fast your engine's spinning. And it usually goes from 0, 1, 2, 3, 4, 5, all the way up to like 8, 9. But that measurement is in thousands. So when you're up at like 6, it's actually 6,000 revolutions per minute. That thing's moving, huh? Moving. Shall we move on? I think we should. I've already eaten up so much class. All right, we're ready to start introducing trigonometric functions. Seven 7.2 is called right triangle trigonometry. In this section, what we're going to do is we're going to introduce you to 6 brand new functions. And I know some of you have heard of them before, but we're acting again as if you have never heard of them. We're going to introduce 6 new functions. And they're all going to be based upon a concept here of a right triangle. This is not the only way you can introduce these 6 functions. There are other ways you can introduce these without using a right triangle. This book does it first by starting with the right triangle, and then the next section they're going to do it a slightly different way. And so you're going to have exposure to the ideas from multiple perspectives. So we're going to start by drawing a picture of a right triangle. And we need to make sure we all understand what a right triangle is. A right triangle is any triangle that has one angle inside that is right. And what does right mean? 90 degrees. Pi over 2. Is it possible to have a triangle that would have 2 right angles? Can you draw a triangle that has 2 right angles? I'm hearing a lot of no. So I'm going to ask you, if you think it's no, I would like an explanation why.
To 180 degrees.
Oh, okay, so you've heard that before? Have y'all heard that before, that if you have a triangle, any triangle, that the sum of the angles has to be 180? Have y'all heard that?
Yes.
Okay, so I'm going to put this as a side note. Any triangle, and I hope that it's okay to assume that you understand a triangle is a 3-sided polygon, 3-sided object. Okay, so a triangle, if you have 3 angles in here, let's call them alpha, theta, and beta, we know that alpha plus beta plus theta must be 180 degrees. That is known and understood? Okay. So it would be impossible to have 2 90-degree angles, because then your third angle would have to be 0, because the 2 90s would already make up the 180. Your third angle would have to be 0, and the only way to be 0 is if these come together, and you wouldn't have a triangle. Right? Okay. I'm going to draw you a triangle with 2 90-degree angles. Ready? Here it comes. So I'm about to break all the rules. You ready? Here it is. This is a sphere. See the sphere? Okay, here's the North Pole. I'm going to travel from the North Pole down to the equator on a straight line going down to the equator. Here it comes. I've hit the equator, right? Now I'm going to travel on the equator in a straight line around, and then I'm going to travel back up to the North Pole. Like that. I'm going to help illustrate this a little bit by bringing in the center of the circle, or the sphere. And I'm going to go like this. Do y'all see that in there? Can you see that? I've almost cut a chunk out of this thing. Y'all see it? Yes. Okay. Now, this angle right here is a 90-degree angle, and this angle right here is a 90-degree angle. This one doesn't have to be, but it depends on how far I walked this way. Like if I came along, if I stopped here and went back up, this up here wouldn't be 90. But this is a triangle that has two 90-degree angles. But hold on, it's a way different triangle than this triangle. This triangle lives on a sphere. Okay? So a triangle on a sphere does not have the same rules that this does. All I'm trying to tell you right now is that the mathematical world that we live in this class, is what we call Euclidean, two-dimensional Euclidean geometry. Everything's on a flat sheet of paper. If we're on a flat sheet of paper, we have to follow certain rules. Here's the rules for triangles. But in general, it does not have to follow that rule. So if you're ever on some millionaire quiz show and they say, the sum of the angles of a triangle has to be 180, true or false? The answer would be false, because you can have triangles on spheres, you can have triangles on all sorts of things. I'll give you another example to see if this helps illustrate my point. Two parallel lines, do they ever intersect? Two parallel lines, do they intersect each other? No, not generally. I mean, not in your life that you've been told they don't, right? I'm going to erase that because everyone said they knew it. Okay, so if I draw a picture, top view of a road, there's a road. Let's imagine this road goes forever, straight line, and then let's say there's some buildings over here. Okay, do these two curbs ever intersect each other? They don't, right? These buildings, right? This wall and this wall, if we extended those forever, that they wouldn't hit each other. Parallel lines don't intersect, right? Not in Euclidean geometry. Well, if anyone has ever taken a drawing class, you've learned about how to draw that picture in perspective, maybe not. You draw a horizon, you draw a vanishing point, you bring your vanishing point back like this, then you bring your street down, then you put your buildings over here, and you make everything that is normally parallel gets all sucked down to the same point. I'll show you what I mean in a second when I finish this. Okay, so, I don't like that. Okay, look at this. This is like caveman drawing versus I'm tricking your eye into believing that's three-dimensional, right? I'm giving depth to the picture. Now, the way I did it is that I violated the rules from Euclidean geometry. To trick you, I had to take the rule of parallel lines don't ever intersect, and I had to make them intersect. So this parallel line, that parallel line, in the real world it's parallel, right? But in perspective geometry, they intersect at a place we call the vanishing point. Has anyone ever seen anything like this before? Okay, so again, all I'm trying to get you to see is that every single thing that we do in here is Euclidean geometry. But it is not the only type of geometry. So if you were so inclined to become more of a math major, you would take entire courses on other types of geometry. You would study you have entire classes called non-Euclidean geometry. Geometry, not this, basically. So there's all sorts of different things. Okay, why am I telling you all this? Why? Because like a lot of things in the real world, you're a fish in a fishbowl. We're all fish in a fishbowl. What we think the real thing, how it is and the way it is just our little world. But you have to understand that there's an entire other things out there that have nothing to do with you. The fish has no idea, right? My daughter's fish has no idea that we have two dogs that live in the backyard, you know? And so if you start talking to the fish about dog, well, if you're talking to your fish, that's already a problem. You get the idea, the analogy. The analogy is that Euclidean geometry is this fishbowl, but please understand there's entire other worlds in mathematics that exist beyond the fishbowl. So when I throw a right triangle up here, it can have one right angle, only one right angle, because we are in Euclidean geometry. Boy, that took me a long time to say that. Okay. Let's label some sides. Let's call this angle in here theta. Let's call this over here O. Let's call this A. And let's call this H. Now, if we do this, these letters I put here for a reason. In other words, I used O, A, and H for a reason. This side of this triangle is the side that is opposite to this angle. So if I'm this angle and I look out, I can see that side opposite of me. And then this side, A, so O stood for opposite. What does the A stand for? Adjacent. Adjacent means like your neighbor is right next to you. And then what does the H stand for? Hypotenuse. And what does hypotenuse? It's opposite of the 90? Okay, but it's always the longest side of the right triangle. It's always the longest side. So you could argue that when you have an angle here, that both these sides are adjacent. But one of them is the hypotenuse. It's the longest side. So the adjacent one is the other one. You could also say it's opposite of the 90. So look at this. If I put beta in here, what is the side that is opposite of beta? A. And the adjacent side to beta is actually O. The hypotenuse is still the same. But I don't want to confuse us. Any questions? All right. Now notice that if I draw this triangle a different way, like this, and call this theta. Theta's grown, right? Theta's gotten bigger. This would be A, this would be O, and this would be H. Different triangle, different. These are different measurements now, aren't they? A's gotten smaller, O's gotten longer. Or I could do something like this. As I change the angle, the sides change. And that means that the ratio of the sides change also. And what we're interested in with right triangles is this idea of creating 6 functions that somehow measure the ratio of the sides. Ratio meaning fraction. If I take this side and divide it by this side, right? Take this and divide it by this, I'm going to get a number. But if I change the angle, I do this side divided by this side again, the number's going to be different. Look at this one. This one is really exaggerated. You can see it. If my angle is really small, this side divided by this side should be big or small? Big number or small number? If I say take this side and divide it by this side, it's going to be a small number because this is small and this is big, right? Take a small number divided by a big number, that's going to be a small number. So please see that as theta changes, this side divided by this side changes. Now, I could have done this side divided by this side. Why not this side divided by this side? Does that change also as I change the angle? Yes, right? How about this side over this side? That changes? How about this over this, or this over this? How many different combinations could I do here? There's 6 combinations. And that is where we get the 6 trig functions from. So let me define what they are, the 6 trig functions. The 6 trig functions are this: sine, cosine, tangent, sorry. What order do I want to go in here? Cosecant, cosecant and cotangent. Those are your 6 trig functions. Now I grouped them together on purpose. It's like I gave you 3 and then I gave you 3 more, right? And the reason why they are grouped, you're about to see, all right? So let me define what they are, and I'm going to get rid of this second one. I'm just going to work on that one. The sine function, which I'll call the first one, sine, first of all, is written this way. Sine, S-I-N, and then inside the argument of the function, you put the angle theta. This is defined to be the opposite side of the triangle divided by the hypotenuse. That's the way we define it. Side note. What type of function is this? Quadratic, right? That would draw a parabola? Yes? What is the name of this function? No, this one right here. Forget that for a second. What is the name of this function? No? We know it's a quadratic. We know if we draw it's a parabola. Do we know the name of it? F. That's the name of that function. That's F, okay? If I call this right here g of x equals x cubed minus x squared plus 1, what's the name of this function? G. This is the g function, all right? This is the g function. What does the g function do? It takes in an x, and then this is what it spits out, yes? When I write sine theta, I want you to understand that this sine is like the g and like the f. It's just the name of the function. How do I let you know I'm talking about the sine function? I frickin' write S-I-N, and then you know I'm talking about sine. You see what I'm saying? It's just the name of it. What do you plug into it? Some angle. What does it spit out? The opposite side divided by the hypotenuse side of the triangle that is formed when you draw it like this. Understand that? So sin, sin, is just the name of the function. Does that make sense? Okay. Now, we have 6 more, or 5 more, sorry. The cosine function is going to be written cos theta. So the name of this is cosine, and it is the adjacent divided by the hypotenuse. So that means you're going to take this side and divide it by this side. Whatever that number is the cosine. The third one is tangent. And you write tan, T-A-N. The argument of the function is theta. And this is going to be opposite. I'm going to start abbreviating. OPP over adjacent, ADJ. Now the other 3, cosecant, secant, and cotangent, the way I wrote them up here is they match up intentionally with sine, cosine, and tangent. All they are these same functions flipped over. So instead of opposite over hypotenuse, we do hypotenuse over opposite. And so the remaining 3, I'll go 4 here, is cosecant. And that is written CSC theta is the reciprocal of sine. So it's hypotenuse over opposite. Fifth one is secant. And this is written SEC theta is adjacent over a hypotenuse flipped over. So hypotenuse over adjacent. And then finally, the sixth one is cotangent. And that's written COT of theta equals adjacent over opposite. Okay, that's exhausting. 6 functions. Now, I heard someone mention, did I hear you say SOHCAHTOA? Okay. How many of you have heard SOHCAHTOA before? What do you know about SOHCAHTOA?
S is for sine, and it's like the way it helps you. It's a way of remembering the 6 trig functions.
Okay, so it's a way that helps you remember these things, and actually, it helps you just remember these first 3, and then if you know these first 3, then you can remember that those 3 are just those flipped over. So SOHCAHTOA. SOHCAHTOA was a brilliant mathematician. She was I believe she was Native American. She was outstanding. She's Pocahontas. She was related to Pocahontas. I'm making this up. When I was in college, I had a girlfriend, and I dressed up as the Invisible Man for Halloween one year, and then she went as Pocahontas, but I made everyone call her SOHCAHTOA that night. That's SOHCAHTOA. So, is that appropriate for me to say that is a Native American name? I'm probably in trouble for saying that right now. But, okay. SOHCAHTOA is a way to remember this relationship. Sine, right? S up there. Sine is opposite over hypotenuse. So, cosine is adjacent over hypotenuse. TOA, tangent, is opposite over adjacent. Do y'all see it in there? So, TOA. It's very convenient, all right? So what I'm going to do now is I'm going to give you an example of finally using this. And then we'll really hit this harder next week. And that should be enough information to have a nice, good quiz. Example here. Let's say that we have this triangle. And I'll use one of our classic ones. Find all 6 trig functions of theta. So I gave you a right triangle, didn't I? And I'm asking you for the 6 trig functions of theta. So that means I want to know what sine of theta is. I want to know what cosine theta is. I want to know tangent, theta, cosecant, secant, and cotangent. I always like to just get the first 3. Because I know that whatever the answers are here, the other 3 are just those flipped over. Do you all agree with that? Okay. So sine of theta, by definition, SOHCAHTOA, so opposite over hypotenuse, should be the opposite side to theta over the hypotenuse, which is 4/5. So be careful. I put theta here intentionally, because most of the time we put it here and then you're just like opposite, adjacent, hypotenuse. But because of the way I drew it, the opposite side to theta is there. The adjacent side is here. And then, of course, the hypotenuse is up there. It's the longest side. So sine, by definition, should be opposite 4 over hypotenuse, which is 5. Cosine? 3 over 5. And then tangent, which is 4 over 3. Opposite over adjacent, 4/3. The other 3, cosecant theta, secant theta, and tangent theta, are just those fractions flipped. Yeah, cotangent, thank you. So this should be 5/4, 5/3, and 3/4. Straightforward. I'm not trying to make this more complicated than it has to be. Any questions on that? Okay, let's try another one. How about this one? Right triangle. 8, 3, x, theta. Find the 6 trig functions of theta again. What's different here? Yeah, the previous problem, I gave you all the sides of the triangle, didn't I? On this one, I didn't give you all of them. I only gave you 2 of the 3. So is there a way you can find x?
Yeah.
How do you get it? Pythagorean? Yep, so you can go back to the idea that you know that on any right triangle, A, B, C, that a squared plus b squared is c squared. So I can take this information here and I can write down an equation on the side here to go help me get x. I can write x squared plus 3 squared equals 8 squared, right? That's what I can write. And I can try and solve this for x. So x squared plus 9 equals 64. Subtracting 9 from both sides, I get x squared is 55. Y'all agree? Now that's what x squared is. What's x? Root 55. Why not plus or minus? I thought that when I took the square root on both sides of an equation, I was supposed to do plus or minus. Because you are supposed to. Because what? What doesn't make sense? Yeah, getting the negative answer doesn't make sense because x is the length of the triangle, the side of the triangle. So technically there is a plus or minus there. Algebraically there is, but within the context of the problem, only the positive answer makes sense. So this is actually root 55. Now you can go do all your SOHCAHTOA. So, yes?
On like radicals like that, do you want us to simplify them more? Like break them up? Do you care?
I mean, if it's like square root of 9, yes. But if it's like square root of
Like
40,
square root 6, stuff like
you don't need to do that. You should be able to, but it's not that important. What's sine theta? 3/8. See, opposite side is this one now. I switched where theta was. In the last problem it was here, now theta's here. So opposite's the 3, adjacent's the root 55, and the 8 is your hypotenuse. So this will be 3/8. And then cosine is root 55 over 8. Y'all agree with that? And then what's tangent? 3 over root 55. I'm going to come back to this in a second. Cosecant is what? Just flip, right? 8/3, 8 over root 55. And finally, root 55 over 3. Please sign in. We still have time. Those are our answers, right? So in these last 6 minutes, I have a question for you about, I'm going to highlight 2 of these here. 2 of these answers are suspect. This one and this one right here. Because the root is in the bottom, right? So let me just look at one of them. 3 over root 55. What is wrong with that? Can't have the square root in the denominator? Who said? No, who said? Who told you? Can you? Is it okay to have a root in the denominator, or do we have to do something to this? Let's take a vote. Let me remind you what I'm talking about. You multiply the top and bottom by root 55. This is called rationalizing the denominator. And what happens is on the top you get 3 root 55, and on the bottom you get what? When you multiply these together you get 55. And see, this expression no longer has a root in the denominator. And I know many of you have been told that you can't do that, you're not supposed to leave it like this. Right? Show of hands, how many of you have been told you're not supposed to leave it like this? Okay? How many of you have been told why you can't leave it like this?
I have, but I don't.
Okay, so the reason I'm telling you this is because there's nothing wrong with this, okay? There's absolutely nothing wrong with this answer. It is correct. Now, we do want to rationalize here because we want our answers to look like what's... We're going to see that those common angles we have, later on there's going to be numbers with those, and we want to be able to match them up. But in general, please, if you're going to take anything away from these last 5 minutes, it's that don't ever go tell someone, I'm trying to stop this from happening. Don't tell someone that you cannot have a root in the bottom, okay? Because you can. And here's why. I'm going to give you the why. Let's take a very simple example like 1 over root 2. If you were told to rationalize this, you would multiply the top and bottom by root 2. What would I get on the top? And on the bottom, what would I get? 2. If I type this into my calculator, I'm going to get the exact same answer that I get if I type this in. They're the same thing. It's about 0.707. I still haven't explained why it's okay, right? So here it comes. Before calculators, before computers, computations like this had to be done by hand. So imagine that you were trying to calculate this by hand. First thing is, you would have to actually have memorized what root 2 is. At least the first 4 or 5 decimal places. So you would have to know in that math class that root 2 is about 1.414. And then what you would do is old school division. You put your division box, you put a 1 here, you'd put 1.414 here, then you would try and start doing division. And it gets tough because 1.414 doesn't go into 1. So you have to bring a decimal up here and put a 0 and then say, how many times does 1.414 go into 10? And then you start thinking, I don't know, what? What do you think, 1.414 into 10? So you might take a shot at it, right? Do you see this as difficult? However, if you do this instead, watch what happens. This is 1.414 divided by 2. You see the difference between those two? If I do this with long division, 1.414, I put a 2 out here. I say 2 doesn't go into 1, so I bring my decimal up. 2 goes into 14, 7 times, and then I'm off to the races, 0, 7. And I can grind this out pretty easily by hand because the number on the outside is a nice integer, as opposed to over here, the number on the outside is an irrational, non-repeating, non-terminating decimal, and that's a mess. Do you see that? Advantage. This is a major advantage if you don't have a computer. We do. It's not necessary, but somehow back then it was ingrained in people's brains. You never want to leave a root in the bottom. You never want to leave it because you're going to need to do this by hand. But somehow that got lost. And now it's just you can't do it, and no one knows why they're saying it. Okay? So technically speaking, this is a correct answer. But I recommend you rationalize denominators because later in calculus, you have to rationalize denominators when these are variable expressions, like 2 over root x. We have to try and get the x out of there, so we have to multiply top and bottom. So the actual technique, the mechanical skill of rationalizing is something you do need. But this is perfectly okay to leave as is. You get the same answer, that you do if you rationalize it. Hope that makes sense. All right, everybody sign in. If you want your quizzes from last time, they're up here. I don't believe it was possible to score under a 70. I think the 70 was the lowest I gave on that quiz. Have a good weekend, everyone.